Okay, this is May 2016, paper 1, question 6. Try it out. Hit play when you're ready. So we are looking at electron configurations here, which means we need to be able to read the periodic table. That's what I always like to call it. We're reading the periodic table for selenium with a 2 negative charge. So we're looking at selenium down here, but we're realizing that it's not an atom of selenium, it is the ion of 2 negative of selenium. So that means I need to remember a few things about ions. A negative ion is because we add an electron. The electrons are the only thing that we can either add or get rid of, because otherwise we're doing nuclear chemistry. So a positive ion is losing electrons. This negative ion is called an anion, just as a refresher. The positive ion is called a cation. I positively love cats. So now getting back to it, we know that we have selenium with a 2 negative charge. That means negative, there's 2 of them. I've added electrons, it's an anion, and I've added 2 electrons. So overall, I'm looking for a total of not 34 electrons like selenium atom would have, but I am looking for 2 more than that, so 36. 36 electrons total. So that would be one way you could go about doing this problem. You could look at the electron configuration and remember what the different parts are, and the superscripted numbers, all of these, equal electrons in those energy levels. So you could look at those and sum them all up, and you could end up finding the one that has 36, and that could be one way that you would solve this problem. The way I'm going to go through it is reading the periodic table as if it were a book. So when I'm reading a book in America, I start in the top left corner right here with hydrogen. And I know that this first row is my first energy level. The second one is my second energy level. Third, going all the way across, is my third energy level. When I get to my fourth energy level, I get a little weird when it comes to this blue sectioned off area. We call it the D block, and we called the first one the S block. We called my pink one the P block, and then we've got this weird one down here, that's the F block. We don't go that far, we're just going up to selenium here. So S, P, D, and F, my D block ends up starting here 1 energy level lower. So it's the third energy level. So even though I've got a 4S here, I'm going to have a 3 there, and then it goes back to the 4P. And then it just keeps going down like that. 5, 6, 7 for the S's and the P's, but we've got a 4, 5, and 6 here. So the S's start with 1. The P's start with the second energy level, the D's start with the third, and the F's start with the fourth. And so as you're counting down, you can think about those things. So the energy levels is the first number, so that's this number here, that's what I was circling over here, that's my energy level, and that's basically how far the electron is from the nucleus. And then I've got the weird little letters, the shapes. S is like a sphere, P is like an infinity symbol, D starts getting funky, kind of clover-like, and then F is just crazy, and you don't have to know the shape of it. So those tell me the shapes that I can likely find, or the density of where I can find my electrons around the nucleus in that energy level. And then those, again, the top number are the number of electrons. So I'm going to start reading through this periodic table, and I've got first energy level, S block, and there's 2 boxes. So I've got one S2, which I've got a 1s2 here, 1s2 here, 1s2 here, 1s2 here. So they're all the same so far. The reason I've got 2 is because each box represents 1 electron, because I'm adding 1 electron with each proton that I add. And a hydrogen is in the first energy level. We just put it over here because it behaves like the other noble gases. So I've got 1s2, and then I go down, because I'm reading a book, I go down to the next level. I've got 2s2, so I've got a 2s2, I made that one look funny, but it's there, 2s2, 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 and then I cross the Great Divide here. I get in the 2p area, and I've got 1, 2, 3, 4, 5, 6, and I still haven't hit scandium, so I'm going to have to keep going after this, but it's 2p6, and so far I still can't rule any out. They all have those. Go down to my next energy level, it's the 3s2. So far so good with all of them. Cross the divide again. I've got 3p, 1, 2, 3, 4, 5, 6, 3p6, 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 3p6. Whew, they're so far, all of them are the same. Going down to my next energy level, here's the 4s2. So I've got 4s2, 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 4s2. And then I've got the third energy level with the D shape. So I've got 3D. I can cross these two off now because it's not the 4D. The levels overlap, which is why they're actually at a lower energy level. And they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. So 3D 10. Ruled out 2, but still have 2 to go. And then I need to think about the fact that normally I would be in the 4p 1, 2, 3, 4 to get to selenium, but I added 2 electrons. So 5, 6, 4p6 to get all the way to what selenium will be when it's got 2 more electrons. And again, you could have done a little bit of a shortcut here, and you could have gone through and just counted up all of those electrons to figure out what the total was. But we can do it both ways. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. And if we were asked, which sometimes we might be, how many valence electrons we have, first we would need to remember what a valence electron was. Valence electron, these are the ones involved in bonding. And they are the outermost electrons, so in the outermost energy level. So if I'm looking at this one, my 4th energy level is my highest one. I said that the superscripts represent the electrons, so I would have to take 2 plus 6 to get 8. There are 8 valence electrons in Se2 negative.